All right. Welcome everybody for joining this session. I'm very glad to see you here online. It's 10 minutes to 2 o'clock and we're approaching the first session of the research track. My name is Jan Mentling and I'm very happy to introduce you to the first speaker, who is Riccardo Galanti, from a team of Spaniards and Italians presenting work on explainable predictive process monitoring. I'm very curious how we can understand better why certain things are observed based on game theory and Shapley values. Riccardo, the floor is yours. Please go ahead.
Thank you very much. Hi, everybody. My name is Riccardo Galanti. I'm a PhD student at the University of Padova, and I also work in Mainvigno. And this paper, called Explainable Predictive Process Monitoring, is actually a joint work between Mainvigno, the Universitat Politecnica de Catalunya, and the University of Padova. In these years, the focus has been mainly in predictive business process monitoring. So starting from an event log, the data is fitted inside a predictive model that could be a machine learning or a deep learning model that is trained on this data in order to predict the outcome of a business case. In these years, the focus has been mainly in the accuracy of this model. And in particular, it has been proved that LSTMs, that are neural networks, can really outperform other methods from an accuracy perspective. The problem is that these models are usually black boxes. So starting from, for an example, a running case, we fit this data inside our black box model, and then we get a prediction like the total case cost will be $40. The problem is that why is the model providing such outputs? We actually don't know. And this paper proposes a possible approach to deal with this problem and to solve this problem. In these years, two main approaches have been proposed to solve this explainability problem. The first, called intrinsic, in which, as you can see, the explanations come directly from the model itself. For example, here, there is a tree-based model that is very, let's say, interpretable. You can understand very well why a person is predicted to be healthy or not. The problem is that these models usually lack of accuracy. The other approach that has been proposed is a post-hoc approach, in which from an input you train your black box model and then you get an output. Then explanations come from an external algorithm that is applied afterwards on top of that. We decided to rely on this kind of approach, and in particular on SHAP. That is an algorithm that has the strong theoretical foundation of the game theory approach, and that can provide very consistent explanations both offline and online. Moreover, is model agnostic, so it can be applied on top of every model. It could be a machine learning as well as deep learning model. I'm providing you an example just to understand how SHAP works. Here we have to predict whether or not a patient will have cancer, with 0 meaning no lung cancer and 1 meaning cancer. And then, of course, there is a probability between 0 and 1. The closer to 0, the less probable it is to have cancer, and the other way around for 1. You can see also the base value below. It is 0.1, so the model is predicting only 10% of the times that the patient will have cancer. Here we are given a patient, so for example, a 65 years old woman that is smoking, and the output the model predicts that this woman has the 30% of probabilities to have lung cancer. Then SHAP is applied on top of that and gives us does a permutation of the features and gives us the relevance of each particular feature. For example, as you can see here, the fact that she's a female is decreasing the probability to have lung cancer, while on the contrary, the fact that she is smoking is increasing a lot the probability to have lung cancer. In our approach, we have two phases. In the offline phase, we focus on the completed cases, and for each prefix of each trace, we generate explanations. So we start, for example, for the first trace, we have all the prefixes for this trace, and for each of them, we provide an explanation. The output of this phase is an heat map in which the most relevant features are shown in the x-axis, on the y-axis. These explanations are saying to us why the model is predicting like that. In the cells, you can see the value that represents how many times a particular feature have influenced the prediction, with red meaning that is increasing the prediction according to the particular KPI. So for example, is increasing the remaining time prediction as an example, while the blue, on the contrary, is decreasing the prediction. Also, the history is important in this model. So on the x-axis, you can see the time step difference. It is the difference between the index of the event from which the explanation was taken and the index of the last event of the current prefix. I will recall you this concept later because it will be clearer with an example. So here, for the sake of simplicity, we have just focused on activities and resources attributes. So in this first example, we have request created that is performed by resource R1, and we see that the explanation is negative, meaning that probably the model is predicting a lower remaining time because resource R1 is a very efficient resource. Then we pass to the second prefix, in which request created is followed by elaborating request that is performed by resource R2. Here we are seeing that the explanation is telling us that the remaining time is increased, probably because instead this resource R2 is not so efficient as R1. Then for the fourth prefix, we see that now we are performing requesting missing information. So we were working on a case, and then we can realize we missed some important information. And this fact increases a lot the prediction, for example, of the remaining time. But we also see that the fact that in the past we performed elaborating requests by resource R2 is still increasing the prediction. This is the concept of time step history I was telling you before. Then in the online phase, for each running case, that is, for example, this, we provide a prediction of a remaining time, for example, and explanation for increasing or decreasing this particular KPI. Our approach is totally generic and model agnostic, so it can be applied on top of every possible algorithm. But here we decided to operationalize it with LSTM, since it has been proved to achieve very great results in considering the accuracy. The pipeline is rather standard, so I won't deep into the details here. I want just to recall you a concept of preprocessing. For example, here for the one-hot encoding concept, here we have an event log, and for each categorical attribute that is, for example, this activity, we produce a different column for each of every possible value. So starting from this single column activity, we produce 3 different columns, one for each value, so one for each activity, and we put a 1 in correspondence to the right column. This concept will be needed later to understand our explanations. So now let's start to dig into the details of our approach. Here we have a very simple process in which a request is being created, then is being elaborated, then either can be finalized or we can request some missing information, and then eventually a back office adjustment is requested, and then the case ends. In this case, we want to predict in advance whether or not this back office adjustment will be performed, because of course we want to avoid that situation. Now let's start with the execution of this process flow. So we start from the first request created that is performed by resource R1, is encoding in the way I just told you in the last slide. Then Shapley values are calculated, and here you have an average prediction that is on average, the average value that is predicting the model. So in general, is predicting 20% of the times that a back office adjustment will be performed. In this case, you have a current prediction that is 10%. So it means that it's lower than the average prediction. And this difference that is called the payout is distributed among all the features, among all that are the Shapley values. Then we take only the explanation that are below the mean minus free standard deviation or above mean plus free standard deviation. In this case, we take the explanation resource R1 that is performing this activity. And so the output of the model is that a back office adjustment won't be performed, and the explanation is because this activity is performed by resource R1. Then we pass to the second activity, is encoded always in the same way, and we calculate the Shapley values. As you can see here, the model instead is predicting that this activity will be performed in the future. It's not so sure, it's a 55% of probabilities, but it's saying that it will happen. This payout is distributed among all the features, and we take, in this case, resource R2 as an explanation, always with the same rule for the explanations that are below the mean -3 standard deviation or above. And then in this case, so the output is that a back office adjustment will be performed, and the explanation is because this activity is performed by resource R2. And we pass to the third activity, that is requesting missing information. Here we can see that the model is rather sure that this activity will be performed. As we can see, 0.95%, so it's rather sure. This payout is distributed, and here we have two main explanations. One is because we have noticed that we missed some important information. So since we are performing requested missing information, then a back office adjustment will be performed, as well as the fact that we are not performing finalizing request. And so this is the output. For an evaluation, we take bank account closure. It is a process executed at an Italian banking institutions that deals with the closure of customers' accounts. This data set has several attributes. I won't dig into too much inside the details. I just want to recall the two important attributes. One is the closure type. It is the procedure carried out for an account holder. That can be bank recess. So it's the bank that decides to close all the bank account of the customer, or the client recess. So it's the client that decides to close all its bank account, or can be inheritance. So for example, the client is passed away. Then there is the closure reason. That could be one client loss, meaning that all the bank accounts of the customer will be closed, or could be two keep bank accounts same deep, meaning that only one among different bank accounts he owns are closed. Here we can see the explanation for the case cost prediction. For other KPIs and other experiments on other public available data sets, please refer to the paper and the appendix complementing the paper. Here we see that the most important attribute that is, and the most important feature that is influencing the prediction is closure reason one client loss, meaning that when all the bank accounts of the customer are closed, then this will yield for higher cost. Then the prediction of the case cost will be much higher. On the contrary, when we have bank recess, so it's the bank that decides to close all the bank accounts of a customer, then the prediction of the case cost will be much lower. So the case cost will be lower. The same happens when only one among different bank accounts are closed. So the prediction, the case cost will be much lower. And another important attribute is activity evaluating request not registered letter. This activity is performed by a resource director that of course yields for higher costs, and also the fact that this activity has been performed in the past, as you can see by this tail, is still influencing the prediction, increasing the case cost. This is an example of the online phase in which we have different running cases, and for each running case we have a remaining time prediction, for example, and explanation that are increasing or decreasing the KPI, in this case the remaining time. Concluding, our framework is able to provide intelligible explanation that can be understood by process actors. The technique is totally independent of the actual AI predictive model, and so it's totally model agnostic. We need in the future to verify with process stakeholders whether or not they would fully comprehend the heat maps and explanations that are provided. And of course, explore some natural language generation techniques to produce more user-friendly explanations for the online phase. Thank you for your attention.
Thank you very much, Ricardo. So I would like to start on behalf of Erika and Mike, and maybe some other colleagues in the session, they were asking essentially questions around specific calculations that are behind these Shapley values. So I might rephrase their questions in the direction of, are there any specific assumptions, for example, that the certain criteria and properties are independent? And what are parameters where you have to take design decisions in order to fit these explanation models?
Okay, actually, all the values are calculated permutating all the features. So all the features compared to each other, where those Shapley values. So of course, this is how SHAP works and permutes all the features to give us the feature importance. Then the reason why we choose to take free standard deviation is because we wanted to take not all explanations, because for example, for LSTMs, since the several attributes can be one-hot encoded, there could be so much explanation to be taken. So we wanted just to take the most relevant one, the most relevant ones. So we decided to take, let's say, in this case, the outlier. So what stands below or above the curve from a statistical perspective. So we took only the explanation that were statistically important for our model. This is why we decided to rely on this mean minus plus three standard deviations.
Okay. So as the question and answer session is very short, I continue with asking questions that you guys pose here in the chat. Dirk is asking, from what we observe from the Shapley values, is there anything that we can feed back into the model? Could it be helpful for improving, for example, a process model?
Actually, we didn't thought about it, but it's actually a good suggestion in the sense that we are pretty confident that, and we checked, of course, that these explanations made sense in the actual process. I mean, for example, that when all the bank accounts of a customer were closed, so the costs were higher or lower, so they actually made sense. We did this evaluation to, let's say, validate our approach. So we are pretty confident that this explanation is what really is guiding, it's really guiding the process. So could be helpful in the future to include this information that we extracted back into the model in order to obtain, to help the model, so maybe to increase the accuracy or whatever. Yeah, could be done in the future, could be helpful. At least to indicate this. All
right, so I also wonder in that direction, so your examples centered around activities and prefixes. So what about integrating other perspectives, such as, for instance, resource information? If you're speaking of a bank loan, you may have a certain amount that is associated with that loan. Did you think about that direction?
Actually, we used all attributes. So the model is trained on all attributes, and as well the explanation. So the Shapley values are calculating for all the possible features that were not encoded. So we also had the resources, the roles, the cost, whatever attribute could be able to, whatever attribute we had, we used for the explanations, as well for the predictions. So it's, let's say, surprising that what came out from the explanation was not maybe other attributes. For example, the roles sometimes happened, but these two, closure type and closure reason, were in this case for the case cost, were the most relevant ones. But of course, we took into account all the other attributes. So I would encourage you to read the paper, also for the remaining time prediction, for example, for the activity occurrence prediction, and also for other experiments on other public available data sets, because in those cases, also other attributes came out. So it is interesting also to see in different contexts what are the most meaningful explanations.
All right. So let me briefly check time. I think we are approaching 10 past. Well, maybe a quick question can still go. I try to combine what Arik and Williams are trying to ask. So what have been alternatives that could have been useful in your scenario, like logistic regression, decision trees, other types of explaining models?
In the sense that for using always sharp or for other possible explainable approaches?
Yeah, more broadly. So what could have been other alternatives that you might have tried out?
We indagated also attention-based models to understand, because I know that some researchers are using that particular approach, but it was a little bit controversial whether it's really interpretable or not, because of course, you know, the information is encoded inside the model, so it's controversial whether it could be interpretable or not. And also we decided to not rely on attention-based model because you could use that approach only on neural networks. So for example, below you cannot substitute the neural network with a tree-based model. So this of course we indagated that. We also indagated some more simpler approaches, like for example tree-based models, but for let's say very small examples, it's very easy to understand why the model is predicting like this. But if you have with the data size that is growing, then you have very big trees. So in that case, it's very difficult to interpret what is guiding the model, because you have thousands of attributes and splits, and it's very difficult. This is what we did. Could be useful in the future also to understand how this to substitute, for example, the LSTM with a tree-based model and to apply sharp on top of that to understand how the explanations change from a tree-based model to a neural network. This could be a future direction.
All right. Thank you very much. I would encourage you, Ricardo, to please also have a look at the written questions and answers, that you may maybe respond to them here in the Zoom chat. There are several more that we could not discuss here. Thanks a lot for posing your questions. Thanks a lot, Ricardo, for this talk.
Thank you too. I will stop sharing.
So thank you so much. And I'm very happy that we have Marcos already on the spot. And we are all very eager to discover patterns in process mining. And there's a particular pattern that connects the first with the second talk. And it's not the general topic area, but also the fact that Massimiliano De Leoni was involved with both papers. And I leave the floor to Marcos to tell us more about their work.
Hi, hi everybody. Thank you, Jan, for the introduction. Hope everybody can hear me. Yes? Okay, perfect. Well, my name is Marcus Dees, and I will present work that was done together with Massimiliano De Leoni from the University of Padua and Laurens Reuling from the Technical University of Eindhoven, the same as where I am from. And the title of our work is the design and evaluation of a process-aware recommender system based on prescriptive analytics. So let's dive in with the question, what is a process-aware recommender system? Well, a process-aware recommender systems are a specific class of information systems that monitor the process execution, predict how process instances will evolve, and give recommendations on which intervention should be enacted to prevent undesired process execution outcomes. Well, a lot of work has already been done on the monitoring and the prediction part. You can find that in our related work section of our paper. So we focus on the recommending part in our research. So what are the objectives of our approach? First of all, what we want to do is we want to improve process performance measured by some KPI. We want to avoid subjectivity in the choice of the interventions. That is, we want to give fact-based recommendations. And we use event logs to base our recommendations on historical process executions. And finally, a lesson learned from a previous research paper is that we need good interventions, because without good interventions, good predictions are actually useless. Now, well, let's go to our approach. It consists the same as the previous speaker of two phases, an offline and online phase. Nothing new there. The first step is to create and encode prefixes, again similar to the first speaker. Since we want to use our technique also on running cases, and we need to be able to deal with every partial process execution. And we also need to encode them, the prefixes, to make them ready to be used as an input for any prediction algorithm. Second, we train the predictor and based on these encoded prefixes, and we generate a process model in the form of a transition system to make sure that we only create recommendations for which we have evidence. And well, a transition system is usually not suitable, but since it's only used internally in our approach and it's not shown to the user, it works actually quite well for our purpose. And well, then the predictor and the transition system are then applied together with a set of running cases to create recommendations for these cases. Well, let's go to the first step, is to prepare the prefixes. Well, we'll start with an event log consisting of at least a case ID, an activity, and the timestamp, and an attribute representing the KPI. In our case, we have a binary KPI. Other attributes are allowed, but not necessary. And we create a data set for our prefixes based on this event log. And we start with the empty prefix for each case. And the attribute values of the first event are copied, including the KPI. Next, we take the first activity and add it to our prefix table, including the attribute values of the first event. And next, we take the first activity and then we take the next activity, which is a B, and add it together with the previous activity, which was an A, as a prefix to our prefix table. So we do this for all cases and activities in our event log. And at the start of a new case, we begin with an empty prefix and we continue until we reach the end of our event log. And from the prefix table, we create encoded prefixes using the standard techniques, for example, the ones that were also presented by the previous speaker. And these encoded prefixes are also split in train, test, and evaluation sets, such that a case ID occurs in only one of these sets. So next, the predictor is trained, and again, we use standard machine learning techniques, and actually I will skip this part for the sake of time. It can all be found in our paper. And so then the next step is to generate a process model in the form of a transition system. And to do that, we first take our previously constructed prefix table, and we will create a transition system based on the set abstraction. Other abstractions like multiset and sequence are also possible. And we start at our first case and first prefix. And this is the empty prefix, and this is represented in the transition system as the empty set. And then we move to the second prefix, which is an A, and we use the directly follows relation to construct our transition system. So the empty prefix is followed by the A prefix. So we add a new state for the new prefix, and we add a transition consisting of the occurrence of the activity A, going from the empty prefix to this new state. And in this way, we construct our transition system. So next we see the prefix AB, which can be reached from A, so with activity B. And finally, for the first case, we have prefix ABC, and we also add this prefix to our transition system in the form of state ABC. Now, in the next case ID, we encounter first the empty prefix, and so we already have this state. We do not change the transition system. Same goes for A, but when we reach AC, we create a new state. AC can be reached with activity C going from A. Finally, we encounter prefix ACB, which, because we use the set abstraction, corresponds to the state ABC. And in this way, we obtain a transition system, which will be used when we are going to create the recommendations. So we got our transition system, our predictor. So the next step is to generate recommendations for the set of running cases. And this step also consists of multiple substeps. First, we determine the possible recommendations for a running case using the running case and the transition system. Then we calculate the predicted effect of each recommendation on the KPI. And we do this for all running cases. And then finally, we present a list to the user with all the recommendations for all running cases, ordered based on the expected change in the KPI and going from big to small. And the user can then decide which recommendation to use or not. So the first step to determine is to determine the possible recommendations. So we use the prefix of a running case in our transition system, and we translate the prefix into a state in the transition system, and we find the state AC here. And from AC in the transition system, state ABC can be reached by activity B. So B is the possible recommendation for our prefix. Well, and then for the next running case, which has prefix A, we again look for state A in our transition system, and from A, both states AB and AC can be reached by respectively activities B and C. So the two activities that can occur when you're in state A become both a possible recommendation for our prefix A. And this way we create a list of possible recommendations for each running case. And when a prefix does not correspond to a state in our transition system, we calculate the distance from that prefix to each state in the transition system. And we use the activities from the states that have the smallest distance as possible recommendations. So we can always find a possible recommendation. Now, next, we calculate the predicted effect on the KPI for every possible recommendation. So we start with a list of running cases, and we use the predictor to calculate the expected KPI value. It's all fictive values, but just to show you how it's done. And next, we add the recommendation to the prefix and code also the combination. So CAB and AB and AC are all encoded. And we use the predictor again to calculate the expected KPI value using this prefix plus the recommendation. And then we can compare both the predictions and calculate the difference in expected KPI value. And finally, we sort the predictions from biggest delta to lowest. And recommendations with a negative expected effect are left out. So we do not recommend anything that might lower the KPI. And the sorted list is then presented to the user, who can decide which intervention should be selected to improve the KPI. So we validated our approach using a case study based on a reintegration process. Well, the aim of this reintegration process is to support customers to find a new job. Services like consults, courses, workshops are offered to the customer. And the company where our case study comes from has on average 300,000 active customers and 2,500 professionals. And our process-aware recommender system, here abbreviated as the PAR system, but we mean the process-aware recommender system, should support then these professionals to select the best next intervention for a customer. But in the end, it's up to the professional to choose. And the KPI that we try to optimize is that a customer finds a new job before the service limit. We use an evaluation approach, which is not part of our framework, but we only use that for this evaluation. And what we did is we used an event log of running cases to generate recommendations. And next, we used a clustering technique to find actually similar cases for every running case. So we use an event log of completed cases to find these similar cases. And for each running case that is its prefix, we find a set of similar cases. So within this set of similar cases, we look for the ones in which the recommendation has occurred and for the ones in which the recommendation has not occurred as a next step. So, and when the recommendation has occurred, we calculate the average KPI value, and we call this the average KPI when recommendation is followed. And when the recommendation did not occur, we calculate the average KPI value. We call that average KPI value when the recommendation is not followed. To do this evaluation, we first we compare the average KPI values when recommendations are followed and not followed. Here you can see the graphs. And we find that following the recommendation is actually related to a higher KPI value of 0.74, which means when the recommendation is followed, a higher percentage of customers finds a new job than when the recommendation is not followed, which has an average KPI value of 0.63. So we also performed an statistical analysis, only looking at cases with a statistically significant difference between the sets of similar cases when the recommendation is followed and not followed. And we found that 39% of the cases, we actually see an improvement when the recommendation is followed. And only by 4% of the cases, we see that the KPI actually gets worse when the recommendation is not followed. So we conclude that overall, our that following the recommendation is better. And this is the way that our process-aware recommender system is actually expected to improve the KPI only using fact-based information from an event log. And to conclude, we have we presented a framework to build process-aware recommender systems where subjectivity is avoided since we use only historical data from event logs. And our case study shows positive expected effect on the KPI. But unfortunately, we did not evaluate our approach using an experiment, but we are still actually quite hopeful that we are allowed to do this within the company. And as a future work, actually, the future work has partly already been, presented by the previous speaker, but as a future work, we wanted to add explanations. And finally, also, we want to improve our predictive model by adding also time-related features, because specifically for this case, we see that having certain meetings early on in the process can be very beneficial. So timing matters for the customers. So that concludes my presentation. Thank you for your attention.
Thank you very much, Marcus. I see some people raising their hand. I invite you to please write your question into the chat window because we will not have enough time to discuss all questions. And then Marcus can answer them in the chat once we complete the session. So what I still want to ask is a question that Graham raised and Rashid is asking in a similar direction. So when we make predictions, isn't that the most critical and important thing to take resource availability and capacity into account? What are your experience in your particular case?
Well, for this specific case, in our case study, which is a reintegration process, of course it's important to have availability of resources, but it's much more important because it's a process, but there's not something like a process model. There's no prescribed model in that sense. We rely fully on the experience of the professionals. So then I think it's much more important that the predictive model has to be good. You have to have good predictions, but it's much more important to have good recommendations. So you have to recommend the right intervention for that customer at that specific time. That's right. the main thing that we wanted to show.
Right. So it's if you look into different dimensions, it's about quality essentially. Yeah? So doing the right decision. Yeah. So I think there's still time for discuss another question that Faria was asking. So how to make this model that you're proposing, how to make it more dynamic and open for learning along the way?
Yeah, well, that's an interesting question, because that's also one of the I think one of the problems that we have not looked at. So what if you, for example, if you implement this system, you start recommending, and then you have this, what data can you, actually what you're doing is then you're spoiling a bit your data when you want to retrain your model. So I don't have an answer for that yet, but I'm aware that that is something we need to we need to find something for. Yeah. So
Yep.
sorry.
No worries. No, very interesting point. So I'm afraid we are already reaching 2:30. I would invite Marcus and all others who are still interested in asking questions to stay a little bit longer. And Marcus, please go to the question and answer board and provide answers to the questions that are still open. With this, I would like to close the official part of that session. I thank Marcus and I thank Ricardo for their talks and you all for your interesting and engaging questions. And please enjoy the break, and looking forward to see you in the other sessions that are still to come. Thank you so much.